Hello all, hope you are doing well. In the last video, we have seen some of the important clauses in section 5 of IS 456-2000 which were related to the limit state method. And in this video, we are going to see the annexure B which is related to the clauses of working stress method. Okay, so now basically there are three types of design philosophies in RCC. They are, first one, working stress method. Second one, ultimate load method, and third one, limit state method. Okay, so now among these three methods, IS 456 is mostly recommending the limit state method. Okay, IS 456 is mostly recommending the limit state method, and it is also recommending working stress method in few conditions. Okay, in few cases it is also recommending the working stress method. Whereas this ultimate load method is completely ignored by the IS 456 because it has its own demerits. Then what is the difference between working stress and limit state method is, suppose now if you consider a beam like this, okay, if you consider a beam like this, then let us say a load of 20 kilonewton per meter is applied on the beam. Okay, let us say a load of 20 kilonewton per meter is applied on the load. Now, in the working stress method, we will design the structure by considering the same amount of the load. Okay, we will design the structure by considering the same amount of the load. Okay, then if you take the limit state method, suppose if this is the beam, okay, now if the load is 20 kilonewton per meter, okay, so here what is the actual load? Actual load is 20 kilonewton per meter. And what is the design load? 20 kilonewton per meter only. But now if you take the limit state method, let us say actual load is 20 kilonewton per meter. Okay, then whatever the design load is there, that will be greater than 20 kilonewton per meter, and that design load is calculated by considering the factor of safety. Okay, it depends on what? It depends on the factor of safety. So the thing you have to understand is, in the working stress method, structure is designed for the actual load or working load which will be there on the structure. But in the limit state method, we will apply a factor of safety and we will design it for the higher load. Okay, so that's the basic difference. Another difference between working stress method and limit state method is, in case of the working stress method, the maximum stresses for which a material can be subjected is called as permissible stresses. Okay, in the working stress method, the maximum stresses for which a structure, which a material can be subjected is called as permissible stresses. And in the limit state method, the maximum stress for which the material is subjected to is called as design strength. It is called as design strength. So whatever the design strength and permissible stresses are there, they are calculated using some factor of safeties. They are calculated using some factor of safeties. So let us see the assumptions of the working stress method. So totally there are 4 assumptions. And remember that working stress method is based on the elastic theory. Okay, based on the elastic theory. Elastic theory in the sense, whatever the loads are applied here, okay, whatever the loads are applied here, they are applied within the elastic limit. Okay, within the elastic limit. Now, if you see the first assumption, at any cross section, plane section before bending remain plane after bending. Already this assumption we have discussed in the previous videos. So as per this assumption, whatever the strain variation is there, okay, whatever the strain variation is there, that will be linear in nature. Okay, that means if you see the strain diagram, suppose this is the cross section here. Okay, this is the cross section here. Then strain varies linearly like this based on this assumption. But remember that based on this assumption, stress need not be varies linearly. Okay, so as per this assumption, what varies linearly? Only the strain. Then the second assumption is all tensile stresses are taken up by reinforcement and none by concrete except as otherwise specifically permitted. So now consider a beam section like this, and here we are keeping the steel like this. Now in RCC there are 2 types of sections. First one is the uncracked section and second one is the cracked section. Okay, first one is the uncracked section, second one is the cracked section. So now when it is uncracked section means there are no cracks in there are no tensile cracks in the concrete. Whenever there are no tensile cracks, whatever the stresses are there, whatever the tensile stresses are there, they are taken by both concrete and steel. Okay, suppose this is the stress diagram here. Okay, so whatever the tensile stresses are there here, they are taken by both concrete and steel. Whereas if you see the cracked section, okay, cracked section means already concrete has cracked in the tensile zone. Once if it cracks, it will not carry any tensile stresses. Okay, once if it cracks, it will not carry any tensile stresses. Instead, whatever the steel is there here, okay, whatever the steel is there here, so only that will carry the tensile stresses. Okay, only steel will carry the tensile stresses. So in case of the cracked section, only steel will carry the tensile stresses. In case of the uncracked section, both concrete and steel carries the tensile stresses. Now the point is, all tensile stresses are taken up by reinforcement and none by concrete except as otherwise specifically permitted. So what is that specifically permitted condition is uncracked condition. Okay, so if it is the uncracked condition, then it will be taken by concrete also. But unless it is mentioned as uncracked section, you have to assume that only reinforcement carries the tensile stresses. And one more point is in RCC, okay, in RCC we always design the cracked section only. We always design the cracked section only because they are economical in nature and steel is very effective in carrying the tensile stresses. Okay, so that's the second assumption here. And the third assumption is the stress-strain relationship of steel and concrete under working loads is a straight line. So here, while discussing the first point, I told that whatever the working stress method is there, that is based on the elastic theory. That means loads are applied within the elastic limit. Okay. So now when the loads are applied within the elastic limit, the point will be stress is always directly proportional to strain. The stress is always directly proportional to strain. Now in the first assumption, I told that strain varies linearly, and here I am saying that stress is directly proportional to strain. So in the working stress method, stress also varies linearly. Okay, stress also varies linearly. Okay, that's the third assumption. Okay, and the last assumption is the modular ratio M has the value of 280 by 3 sigma CBC. If you see in the strength of materials, okay, if you see in the strength of materials, the formula for the modular ratio is Young's modulus of the stronger materials divided by Young's modulus of the weaker material. Okay, now in case of RCC, what is the stronger material? Steel. So you can take like E steel by E concrete. So this has to be the actual formula of the modular ratio. But in the working stress method, the formula given is M equal to 280 by 3 sigma CBC. Okay, so for the formula given in the working stress method, that consider the long-term effect such as creep partially. So remember that the formula of M equal to 280 by 3 sigma CBC, that formula is given by considering the partial effect of the creep. So these are the 4 assumptions of the working stress method. So next one is table number 21, which is the permissible stress in concrete. Now in working stress method, I told that the materials are always subjected to a stresses less than the permissible stresses of the material. So now the permissible stresses in bending compression are different and direct compression are different. The member is subjected to bending compression. The member subjected to bending compression is beam. The member subjected to direct compression is column. Okay, so while designing the beams or slabs, these are the permissible stresses in concrete we have to use, and while designing the columns, these are the permissible stresses in concrete we have to use. Okay, then whatever the factor of safety is there, that is almost 3 here and that is almost 4 here. Okay, so just the strength of the material divided by 3, that will give you these values, and if they are not rounded up to 0.5, you have to take the nearest value. Okay, you have to take the nearest value. Okay, then whatever the direct compression is there, for that factor of safety is 4, so you have to take like grade of the concrete divided by 4, that will give you the permissible stresses in the direct compression. Okay, then these are not that important, so you don't need to remember them. Whatever the permissible bond stress is given here, they are for plain bars in tension. But if you are using, okay, if you are using them in the compression, these values has to be increased by 25%. So whatever the value is given here, if you are using if you are using the bond, if you are using the bars in the compression zone, then you have to increase them by how much percentage? 25%. Okay, then the next one is related to the permissible stresses in the steel reinforcement. Okay, so here basically we use two types of bars mainly. One is the mild steel bars and another one is the HYST bars. Okay, so here this is related to the Fe415 and this is what mild steel bar means, Fe250, and you don't need to remember anything about this medium tensile steel. Now if you take the tension, okay, if you take the stresses, if you take the permissible stresses in the tension, it depends on the bar diameter. Okay, it depends on the bar diameter. For bar diameter up to and including 20 mm, permissible stresses is 140 and over 20 mm it is 130. Suppose if it is Fe415, then irrespective of the bar diameter, the permissible stresses in tension is taken as 230 Newton per mm square. Okay, then if you see the bars in the bars in the columns, okay, if you see the bars in the columns, that means they are subjected to what? Direct compression. They are subjected to direct compression. So in that case, permissible stresses in Fe250 is 130, whereas in Fe415 is only 190. Okay, in Fe415 is only 190. Next one is compression in bars in a beam or slab. That means if the bars are in bending compression, then permissible stresses are taken like 1.5 times the modular ratio or sigma SC, whichever is lower, the calculated compressive stress in the surrounding concrete. Let us say calculated compressive stresses in the surrounding concrete is sigma C. So sigma C into 1.5 into M or sigma SC, whichever is lower we have to take. So lower of these two values taken as permissible stresses if the steel bars are there in the bending compression. Okay, then suppose if the compressive resistance of concrete is not taken into account. Okay, so here in this one we are considering the compressive strength of concrete into the account. But if you are not considering that compressive strength of concrete also, usually we ignore the tensile strength only, but here we are ignoring the compressive strength also. So in that case, if the bars are of diameter up to 20 mm, the permissible stresses is 140. If it is over 20 mm, then permissible stresses is 130. Okay, same as the bars in tension only. Okay, then in case of the Fe415, it is not more than 190. Okay, just like this, columns only. Like this, you have to consider permissible stresses in both concrete and steel. Now, instead of using Fe415 bars, okay, if you use the Fe500 bars in the direct tension and flexural tension, then this value has to be 0.55 Fi. Simply that means 0.55 into 500 we have to take. Okay, that is how much? 275. Okay, so if you are using the Fe415 bars either in direct compression or bending compression, the value will be how much? 0.55 Fi. Next clause is clause B2.1.1. So this clause says that where stresses due to wind, temperature and shrinkage effect are combined with those due to dead, live and impact load, the stresses specified in table number 21 may be exceeded up to a limit of 33.33%. Wind and seismic forces need not be considered as acting simultaneously. So here we have to remember a point that whatever the stresses given here, okay, permissible stresses given here, they are applicable when you are considering only dead load, live load and impact load together. But beyond that, if you are using the wind, temperature and shrinkage effects for the design of the structures, then whatever the permissible stresses given here, they can be increased by 33.33%. Then it is also saying that the wind and seismic forces need not be considered as acting simultaneously. Okay, the probability of occurring both wind and seismic forces simultaneously is very rare, very rare. So the IS code says that you need not consider them simultaneously. You have to consider only maximum of those two values. Okay, so this is about the important clauses in the working stress method, that is the annexure B. In the next video we will see the important clauses in the remaining annexures. Hope you enjoyed the video. If you like our video, please share it to your friends and please subscribe to our YouTube and Telegram channel. The link were given in the description. Thank you. Hello all, hope you are doing well. In the last video we have seen the annexure B of IS 456, which was related to the working stress method. And in this video we are going to see the annexure D and E. So here annexure D is related to the design of two-way slabs. Okay, annexure D is related to the design of two-way slabs and annexure E is related to the effective length of column. So basically what is a two-way slab? Suppose this is the slab here, and if it is supported on all its four edges, if the slab is supported on all its four edges on the beams like this. Okay, so here these are the beams. So if it is supported on all its edges like this, and if the Ly by Lx ratio is less than 2, okay, the Ly by Lx ratio is less than 2, then a slab is treated as the two-way slab. So let us see the annexure D first, which is related to the design of two-way slabs. So now the clauses start with D1 point. Okay, the clauses start with D1 point. They are related to the restrained slabs. Okay, they are related to the restrained slab. Whatever the clauses start with D2 point, okay, D2.1, 2.2, these things are of the simply supported slabs. Okay, so whatever the clauses I am going to discuss now, they are starting with D1.1, they are related to the restrained two-way slabs. So what is the difference between restrained and simply supported is? Okay, what's the difference between restrained and simply supported is? If it is restrained, at the edges what happens? Negative bending develop. Okay, if it is restrained at the edges, negative bending moment develop. If it is simply supported, okay, if it is simply supported, then what happens is throughout the span only positive bending moment will be there. But here what happens, at the edges negative will be there, negative bending moment will be there, and at the middle span so you will have the positive bending moment. Okay, that's the point. Now if you take a restrained slab, the maximum bending moment per unit width in a slab are given by the following equations. So as you know, in the two-way slabs, bending is considerable in both direction. You have to determine the both mx and my, and for them you have to design the main reinforcement. So now to determine the mx, the formula is alpha x into WLX square, and to determine the my, the formula is alpha y into WLX square. So now you can observe that while calculating both mx and my, what we have to use? We have to use Lx only. But what is varying here? Alpha x and alpha y. Okay, for calculation of mx we have to use alpha x. For calculation of my we have to use alpha y. Usually the value of alpha x will be always greater than or equal to alpha y. Okay, remember that alpha x will be greater than or equal to alpha y. So most of the times mx will be greater than or equal to my. Okay, that's the point. Okay, so whatever the short span is there, that has to be designed for the bending moment of mx. Whatever the long span is there, that has to be designed for the bending moment of my. Okay, so see the next one. So as I told earlier, as these are the clauses related to the restrained slab, you have to design for both positive and negative bending moment. Okay, now the point is, if you take a slab like this, okay, if you take a slab portion like this, it is divided into middle strips and edge strips. Okay, middle strips and edge strips. Middle strips are usually designed for the positive bending moment and edge strips are designed for the negative bending moment. Okay, now what the class is saying that whatever the middle strip is there, its width will be 3/4 of the total width. Okay, whatever the width of the middle strip is there, its width will be 3/4 of the total width. Okay, then whatever the width of edge strip is there, that is 1/8 of the total width. Okay, so this edge strip is 1/8 of the total width, this is 1/8, so it will be like 1/8 of the width, and this is 3/4 of Ly, and this is again 1/8. So totally how much it will be? Ly. So which is this total width. Okay, okay, now if you take in this direction also it will be same. If you take along the short span, this total length is Lx. So width of the middle strip will be how much? 3/4 of the Lx, and width of the edge strip will be 1/8 of the Lx, like this it is. Okay, so middle strips are designed for what? Positive bending moment, and edge strips are designed for what? Negative bending moment. Okay, that's the point. Okay. Then next classes are related to the reinforcement. Next classes are related to the reinforcement in two-way slabs. So let us see that. Okay, now first I will explain in the diagram, then I will go back to the clauses. Okay, now when you take a slab like this, this is not a beam here, this is the section of slab. So when this is the section of the slab, so whatever the middle strip is there, okay, whatever the middle strip is there, that has to be designed for what? That has to be designed for the positive bending moment. So when it is positive bending moment, where we have to keep the tension reinforcement, we have to keep it below the neutral axis. That means you have to keep at the bottom. So whatever the middle strip is there, that is designed for the positive bending moment. So you have to place the reinforcement at the bottom like this. Now at the middle exactly, let us say the reinforcement you have provided is AST. Okay, at the middle exactly the reinforcement you have provided is how much? AST. So now here the bending moment is high, for that the steel amount is AST. But if you take the bending moment here, okay, if you take the bending moment here at this edge, it will be 0 actually, because it is a discontinuous edge. Okay, it is a discontinuous edge. So here the bending moment will be 0. So now for the bending moment of M, you are providing the area of the steel as AST. So if the bending moment is 0, do you need to provide any steel here? Actually speaking, no. So for that purpose, what code is saying that, so now whatever the positive reinforcement you have designed for the middle strip, it has to be extended up to the length of, okay, it has to be extended up to the length of 0.15 L1. Okay, that means suppose the support to, okay, the mid of the support to, somewhere here the length is 0.15 L1. Okay, so this AST of the area has to be extended up to the length of 0.15 L1 here, when it is the discontinuous edge. Suppose if it is the continuous edge like this, okay, suppose if it is the continuous edge like this, okay, when it is the continuous edge, you have to extend it till the length of 0.25 L1. That means this length is 0.25 L1. So whatever the AST you have designed here, that has to be extended up to this length. Okay, then beyond this point, okay, beyond this point, you have to provide 50% of the reinforcement. Okay, so whatever the AST is there, in that you have to provide 50% here. So whatever the remaining reinforcement is there, that can be bent up like this. Okay, that can be bent up like this. Okay, so that's the point. Okay, so let us see the clause. Tension reinforcement provided at midspan in the middle strip shall extend it in the lower part of the slab to within 0.25 L of a continuous edge or 0.15 L of a discontinuous edge. Okay, so see this again, whatever the tension reinforcement you are providing here, that you are extending up to 0.15 L1 if about the discontinuous edge and 0.25 L1 about the continuous edge. So now see the second point. So whatever this middle strip is there, that is in that what bending moment develop? Positive bending moment. But now whatever the edge strips you take, okay, whatever the edge strips you take, in that what bending moment develop? Negative bending moment. So when the bending moment is negative in nature, you have to provide the tension reinforcement at the top. Okay, tension reinforcement you have to provide at the top. Now whatever the tension reinforcement you have provided at the top here, whatever the tension reinforcement you have provided at the top here, so this total reinforcement has to be extended. Okay, the total reinforcement has to be extended beyond the support to the length of 0.15 L, and 50% of this reinforcement has to be extended to the length of 0.3 L2. Similarly, whatever the tension reinforcement you have designed in this span, okay, whatever the tension reinforcement you have designed in this span, this has to be extended beyond the support to the length of 0.15 L on this side, and in this reinforcement 50% that has to be extended till the length of 0.3 L. Okay, like that it is. Okay, so see this clause again. Over the continuous edges of a middle strip, The tension reinforcement shall extended in the upper part of the slab, that is at the top of the slab, to a distance of 0.15 L from the support, and at least 50% shall extend at a distance of 0.3 L. Okay, so hope this point is clear. Whatever the tension reinforcement you are providing at the top, that has to be extended beyond the support to the length of 0.15 L completely, and in that at least 50% has to be extended till the length of 0.3 L2. Okay, next class is at a discontinuous edge. Okay, at a discontinuous edge, negative movement may arise. Okay, so usually if it is the discontinuous edge, which is like this, then here the bending moment will be 0. But in certain condition, negative moment may arise here. So for that, what IS code is saying that negative moments may arise. They depend on the degree of the fixity at the edge of the slab. But in general, tension reinforcement equal to 50% that provided in the mid span, extending 0.1 into the span will be sufficient. Okay. So now the point is, whatever the AST you have designed here, in that 50% has to be provided at the top in the discontinuous edge, and that has to be extended. Okay, that has to be extended to the length of 0.1 L. Okay, this is not clearly visible here, but this is 0.1 L. So whatever the main reinforcement you have designed here, in that 50% of the steel you have to provide here, and that has to be provided till the length of 0.1 L beyond the support. Okay, beyond the, so these are the three clauses to provide the reinforcement in the two-way slabs. So these next clauses are related to the torsional reinforcement. Okay, now what I am doing is I am considering a slab like this. I am considering a slab portion like this. Okay, then in this slab portion, beams were like this. Okay, totally this is the slab, and in that beams are like this. So now each square or rectangle is considered as a portion here. Okay, each square or rectangle is considered as a portion. So these are what? These are beams. Okay, this is also beams, of course. Okay, now the thing is, if you take this first slab here, and this is the corner here. Okay, this is the corner here. So now whatever the corner is there, whether it is continuous in nature or discontinuous in nature. Okay, so whatever the corner is there, it is discontinuous in nature, because this side there is no slab and this side there is no slab. Okay, now if I say this, once is suppose, okay, that means first slab corner. Okay, first slab corner. So if I take this corner here, then whenever I apply the load on the slab, okay, whenever I apply the load on the slab, what happens is these corners try to lift like this. Okay, the corners try to rotate, the corner tries to lift. So because of that rotation, what happens is torsion will be developed. Okay, because of that torsion will be developed. Now whenever to resist this torsion, what we have to do, again we have to provide the reinforcement. So here, how to provide that reinforcement at the corners is, you have to form a square with the side of 0.2 Lx. Okay, you have to form the side we have to form a square with the side of 0.2 Lx. So this length should be 0.2 Lx, and this length should be also equal to 0.2 Lx. So in this area of 0.2 Lx, we have to arrange the bars in both the directions like this. Okay, we have to arrange the bars in both the directions like this. Now whatever the area of the steel you provide here, that should be equal to 3/4 of the ASTX. Okay, that is equal to 3/4 of the ASTX. So this 3/4 of the ASTX you have to provide in 4 layers totally. Among these 4 layers, 2 layers you have to provide at the bottom and 2 layers you have to provide at the top. Okay, so remember that when the corner is discontinuous on both the sides, then 3/4 of the AST has to be 3/4 of the ASTX has to be arranged in both the direction, and this has to be kept in the square side of 0.2 Lx, and it has to be totally provided in 4 layers, 2 layers at the bottom of the slab and 2 layers at the top of the slab. Okay, now suppose if you take the corner here. Okay, if you take the corner here, So then the corner was like this. So this side of the corner is continuous in nature. Okay, this side of the corner is continuous in nature and this side of the corner is discontinuous in nature. Now when the corner is continuous on one side and discontinuous on another side, then what we have to do is again we have to provide the reinforcement to resist the torsion, and now we have to provide only 3/8 of the AST. Okay, we have to provide how much of the steel? Only 3/8 of the AST. Okay, then suppose you take the corner here. Okay, you take the corner here. Now I am applying the load. Okay, I am applying the load on the beam on the slab like this. Then whatever the corner is there, okay, whatever the corner is there, whether that will be lifted up. Okay, this is 5C suppose. Okay, whatever the corner I am taking here, whether they will be lifted up when the load is applied? No, because whatever the corner is there, it is continuous, it is completely restrained on all the sides here. So when it is restrained completely, it cannot lift it up. So in this condition, you need not provide any reinforcement. Okay, you need not provide any reinforcement. Now when the corner is continuous on both the sides, okay, when the corner is continuous on both the sides, then you don't need to provide any torsional reinforcement. When the corner is continuous on one side and discontinuous on another side, you have to provide 3/8 of the ASTX. When the corner is discontinuous on both the edges like this, then you have to provide 3/4 of the AST. Okay, so these are the clauses about the torsional reinforcement. Okay, then next one, at least 50% of the tension reinforcement provided at midspan should extend it to the supports. Okay, so these clauses are related to what? D2.1. At the starting itself I told that the clauses start with the D2 point, they are related to the simply supported slabs. Okay, now what is this clause is saying? That whatever the simply supported slab is there, in that suppose at the midspan you are providing AST. Okay, at the midspan you are providing AST. Then in this 50% has to be extended. Okay, then 50% in that 50% should extend into the supports like this. Okay, whatever the reinforcement you are providing here, in that 50% you have to extend into the support. So next one is annexure E. So this annexure E is related to the effective length of the compression member. Okay, it is related to the effective length of compression member. So basically, suppose if you take two floors like this, okay, if you take two floors like this, and if there exists a column like this, so this total length of the column is called as unsupported length. Okay, the total length of column is called as unsupported length. Okay, then what is effective length is? Okay, what is effective length is, suppose if this column is subjected to buckling. Okay, or else if the column is subjected to bending, let us say, okay, column is subjected to bending. So when the column is subjected to bending, its elastic curve may be like this. Okay, its elastic curve may be like this, and this depends on purely. Okay, this elastic curve purely depends on the support conditions. Okay, now in the elastic curve, wherever the curvature changes its sign, okay, wherever the curvature changes its sign, that is called as point of inflection. Okay, that is called as point of inflection. So the distance between two point of inflections, okay, the distance between point of inflections in a column, that is called as effective length. Okay, so unsupported length means it is the floor to floor height, whereas effective length means it is the distance between the point of inflections. Okay, inflection means wherever the elastic curve changes its sign. Okay, so now you know what is effective length. So let us see what is the effective length of the column for different support conditions. So now if you take the first condition, column is effectively held in position and restrained against rotation at both the ends. Okay, so here it is effectively held in position and it is restrained against the rotation. So that is there in both the ends. Okay, so P I am using that it is positioned, R I am using that it is restrained against the rotation. Okay, so here also. Now the column is effectively held in the position and restrained against rotation at both the ends. That means it is kind of fixed beam. Okay, so here we can call it as fixed column. So now if it is fixed on both the ends like this, then theoretical value of effective length is 0.50L. Like if you see the elastic curve, then here there may be 1 point of inflection, here there may be 1 point of inflection. So this effective length will be equal to how much? 0.5L. But whatever the value recommended by the IS code, okay, whatever the value recommended by the IS code for the design purpose is how much? 0.65L. Okay, so whatever these theoretical values are there, these theoretical values you have seen in the strength of BTPLs, and these values are recommended by IS 456 for the purpose of the design. Okay, then I am releasing a rotation here, suppose. Okay, I am releasing the rotation. That means it is effectively held in the position, but I am releasing the rotation here. Then other end is effectively held in the position and restrained against the rotation also. Now whenever I release a condition here, okay, whenever I release a condition here, then what happens is effective length increases, because whatever the point of inflection is there, that will move in the upward direction. Okay, that will move in the upward direction. So here one point of inflection may be there, and here another point of inflection, may be there. So that's why the theoretical effective length is how much? Slightly increasing by this value, that is 0.70. Then whatever the recommended value for the design is how much? 0.80. Now if you take the third one, effectively held in position at both the ends, but not restrained against the rotation. Like this is the simply supported condition, we can say. Here it can rotate at this end, here it can rotate at this end. So in this case, one point of inflection is this one, another point of inflection is this one. So straightly, what will be the theoretical value of the effective length? 1L, and the recommended value is also same. Now remaining 4 also, it will be in the same way. Okay, so if you see at this end, it is effectively held in the position and restrained against the rotation, but at the other end restrained against the rotation but not held in the position. There is no P here, okay, not held in the position. So in this case, the theoretical length is 1L and effective recommended value length is 1.20L. Okay, next one is effectively held in position and restrained against rotation at one end. Here it is effectively held in position and restrained against rotation, and at the other end what happens is it is partially restrained against the rotation. It is completely restrained against the rotation in the above case, but here it is partially restrained against the rotation. So I am using like RP. Okay, so in this case there is no theoretical value, but the recommended value by the IS code is 1.50. Okay, next one is effectively held in the position at one end but not restrained against rotation. Okay, effectively held in position against the. Okay, next one is effectively held in position at one end but not restrained against the rotation. Here held in position but there is no rotation, and at the other end restrained against rotation. Okay, so here restrained against rotation but not held in the position. So in this condition, what is the theoretical effective length is 2L, and the recommended value of the effective length is also 2L. And last one is effectively held in the position and restrained against rotation at one end. Here at this end effectively held in the position and restrained against the rotation, and at the other end not held in the position nor restrained against the rotation. So there is no condition of positioning here, there is no restriction against the rotation here. So in this case, what is the theoretical effective length? 2L, and effective and recommended value of the effective length is also 2L. So this is about the effective length. So what is effective length of the column? It is the distance between the point of inflections of the elastic curve. So with decreasing in the restraints, what is happening to the effective length of the column here? Effective length of the column is increasing. So this is about the annexure D and annexure E. And in the next video, we will discuss the last annexure, which is annexure G, and that gives the provisions for the calculation of moment of resistance of beams. Okay, so hope you like this video. If you like the video, please share it to your friends. And please subscribe to our Telegram and YouTube channels. The link were given in the description. Thank you. Hello friends, hope you are doing well. This is the last video of the explanation of IS 456-2000. And in this video, we are going to discuss the annexure G, which gives the formulas to calculate the moment of resistance. Okay, so let us see. So first, let us know what is moment of resistance. First, let us see what is moment of resistance. Okay, so now suppose you take a simply supported beam like this and apply UDL throughout the span. You can apply UDL throughout the span. So when you apply the load like this, then beam is subjected to some bending. The beam is subjected to some bending. So bending in the sense, what is generated in the beam? Bending moment is generated due to the applied load. Okay, bending moment is generated due to the applied load. So now let us say you have used very thin section. Okay, you have used very thin section and you have applied very higher loads. Okay, you have applied higher loads on the beam. So then in that case, what happens to the beam? Whether this beam will resist the applied load? No. Okay, because whatever the loads you have applied, they will cause the higher bending moment, and because of that, because of weak section here, okay, because of the weak section here, this will not resist the applied bending. Okay, so now the point is, whatever the loads you are applying on the beam, they are causing the bending moment. Now in order to resist the bending moment, whatever the beam is there, that should have some resistance capacity. Okay, so the resistance of the beam, or is the resistance of the section against the bending. Okay, resistance of the section against the bending, that is called as moment of resistance. Okay, so now how does this moment of resistance comes is, okay, now consider a singly reinforced section. Okay, this is the singly reinforced section, and in this singly reinforced section, whatever this portion is there, okay, whatever this portion is there, this will be under compression. Okay, this will be under compression. That means above the neutral axis, whatever the concrete is there, that will be under compression, and whatever the steel bars are there here, they will be under tension. Okay, so above the neutral axis, concrete is carrying the compressive stresses. Below the neutral axis, steel is carrying the tensile stresses. Okay, now the thing is, if the beam is in equilibrium, compression force is always equal to the tensile force. The compressive force is always equal to the tensile force. Okay, so now whatever the compressive force is there, for that the centroid is here. Okay, whatever the compressive force is there, for that centroid is here. So this centroid is located at a distance of 0.42 XU. Okay, whatever the centroid is there, that is located at what distance? 0.42 XU from the extreme compression fiber here. And then whatever the centroid of the tensile force is there, is located at a distance of d from the extreme compression fiber. Okay, so remember that this compressive force is acting at a distance of 0.42 XU from the extreme compression fiber, and this tensile force is acting at a distance of d from the extreme compression fiber. Okay, so let us say compressive force is acting at this point and tensile force is acting at this point. Okay, so this distance is how much? 0.42 XU, and this whole distance is how much? D. Then what will be this distance here? D minus 0.42 XU. Okay, now the thing is, if you take two forces, which are opposite in nature and same in magnitude. Okay, if you take two forces which are opposite in nature and same in magnitude, let us say this force magnitude is F, this force magnitude is also F. Then this, when you apply these two forces on a member, that will cause what? That will cause a couple. Okay, that will cause a couple. So what is the formula for the couple? Couple equal to force into distance between the forces. Okay, distance between the forces. So let us say distance is d here. So F into d, or else capital D. F into d. So now in this case, whatever the two forces are there, they are equal in nature and they are opposite in nature. So these two forces will generate the couple here. Okay, now because of this couple, beam will get the resistance. Okay, beam will develop the resistance against the bending. Okay, so what will be the moment of resistance is moment of resistance equal to couple, and that couple equal to how much? Force into, that force is either compressive force or tensile force. Okay, so C into lever arm. Okay, lever arm means nothing but distance between the centroid of compression force and centroid of the tensile force. Okay, or else the distance between the two forces. Okay, that is called as lever arm. So C into D minus 0.42 XU or T into D minus 0.42 XU. Okay, so like this we can calculate the moment of resistance of the beam. Okay, so moment of resistance means the formula is compressive force or tensile force into lever arm, that gives us the moment of resistance of the beam. Okay, now while to determine the moment of resistance of the beam, the first thing you have to determine is you have to determine the depth of the neutral axis. Okay, you have to determine the depth of the neutral axis. So depth of neutral axis is determined from the following equation for the sections without the compression reinforcement. So when I say sections without the compression reinforcement, that means it is which kind of beam? It is the singly reinforced beam. So this clause is applicable for the singly reinforced beam. So in case of the singly reinforced beam, the depth of the neutral axis is calculated using this formula. XU by D equal to 0.87 Fi into AST divided by 0.36 FCK into B into D. Okay, actually what is the formula for the compressive force? 0.36 FCK into B into XU. What is the formula for the tensile force? 0.87 Fi into AST. So now if you, using this, if we find the XU by D value, you will get the same expression which is like this. So the first thing you have to do while calculating the moment of resistance is you have to calculate the XU by D value. Now once if you calculate that XU by D value, if the XU by D is less than the limiting value means XU limit by D value. Okay, so if the calculated XU by D value is less than XU limit by D value, so this XU limit by D value you can get from the clause number 38.1 F. Okay, clause number 38.1 F. So if you compare this XU by D value with XU limit by D value, then if it is less than this value, you have to calculate the moment of resistance using this equation. Okay, now whatever the moment of resistance you have calculated here, what is the basic formula I told? Compressive force or tensile force into lever arm. Okay, so now the tensile force is how much? 0.87 Fi into AST. Lever arm is how much? D minus 0.42 XU. Okay, now whatever the XU is there, for that you can use this formula. Okay, and if you substitute that XU here, then the total formula will be obtained in this manner. Okay, so now one more thing is, whenever XU by D is less than XU limit by D, that comes under which type of section? That comes under the under reinforced section. Okay, see the next one. If the value of the XU by D is equal to the limiting value, okay, now XU by D is equal to the limiting value or maximum value, XU max value, both are same. So if XU by D equal to XU max by D, then we have to use this expression to determine the value. Okay, so now again it is the same thing. Okay, whatever the compressive force is there, that is 0.36 FCK into B into XU, and lever arm is D minus 0.42 XU. Okay, now the thing is, if you do modifications here again, that means take D common here, then you will get the same formula. Okay, so like that you have to determine. Okay, then if XU by D is greater than the limiting value, okay, the XU by D is greater than limiting value. If XU by D is greater than XU limit by D value, then section should be redesigned. So why the section should be redesigned? Because if this is the condition, the section becomes the over reinforced section. The section becomes the over reinforced section. And you have to understand that in the limit state method, over reinforced sections are not allowed because they will show the brittle failure. They will show the brittle failure. So, okay, so for that purpose, you have to avoid the over reinforced section. So we have to design either under reinforced section or balanced section. Okay. Then next one is for the beams, for the sections with the compression reinforcement. For the sections with the compression reinforcement. So when I say section with compression reinforcement, that comes under which beam? Doubly reinforced beam. Okay. Now see the clause. Where the ultimate moment of resistance of section exceeds the limiting value mu limit, compression reinforcement may be obtained from the following equation. Now the thing is, the moment of resistance you required for a section is mu. Okay, suppose you have that section, and for a given section, irrespective of the percentage of reinforcement you provide, okay, irrespective of the percentage reinforcement you provide, mu limit value will be same. Okay, I mean if the for the given dimension, okay, for the given dimension, for given grade of concrete, for given grade of steel, irrespective of the percentage of AST, okay, irrespective of the percentage of AST, mu limit value is constant. Okay, now for the given section, you require the moment of resistance of mu, but the mu limit value is less than that. Okay, mu limit value is less than that. Then the additional moment carrying capacity required is how much? Mu minus mu limit. See this carefully. The actual moment of resistance required is mu, but the given section is offering the moment of resistance of mu limit only. In that case, whatever the additional moment carrying capacity you require, that is how much? Mu minus mu limit. Okay, so in this case what we do is we will provide the reinforcement in the compression zone also. Okay, we will provide the reinforcement in the compression zone also. Now whatever the reinforcement you provide in the compression zone, that will give us the additional moment carrying capacity. So this area of the steel, okay, this area of the steel is calculated using this formula. So what is FSE is, that is the stress in the compression steel. Okay, FSE is the stress in the compression steel, and ASC is area of the steel in the compression, and D minus D dash. D already you know, that is the effective depth of the section, and what is D dash is, D dash is the effective cover for the compression reinforcement. Effective cover for the compression reinforcement. So using these values, you can calculate the area of the compressive steel required. Okay, so this is about the calculation of moment of resistance for the singly reinforced beams and doubly reinforced beam. Okay, so with this IS 456 is completed. So in the coming videos we are going to discuss the IS 1343 2012, that is the code for the pre-stressed concrete. Okay, hope you enjoyed all the videos of this series of IS 456 2000 detailed explanation. So please share it to your friends and subscribe to our YouTube and Telegram channel. The link were given in the description. Thank you.